The aim of this presentation is to introduce key concepts of gradient. Gradient is a very important concept in vector structure mechanics. Correspondingly, gradient plays a very important role in advanced structure mechanics. Before starting gradient, we will have to introduce another topic which is called directional derivative. Directional derivative help us to understand the importance of gradient. Now let us refresh our memory about the rate of change of function in a single variable problem. So if we have a function y is equal to f of x and f of x is shown on the y-axis, x is shown in the horizontal axis. We discussed that calculus or differential calculus is rate of change of function. So imagine we are going from point x to point x plus delta x, and we are interested in finding out the way the function f of x is changing. So we write f of x plus delta x minus the function where we started from, that is x, everything divided by the step size, which is delta x. Then we make the step size close to zero. So in other words, we take a limit, and this whole system gives us differential of a function with respect to x. This is also called as a rate of change of function corresponding to x. Please remember, x is a independent variable. This function can also be written as d by dx of f of x plus delta x when delta x equal to 0. So if we put delta x equal to 0, we get exactly the same thing as this one. This sort of presentation will be very useful when we discuss gradients. Now, rate of change of function is important to find out the peaks and valleys in the function. If we want to find out the maximum value of a function, we can find out df by dx at different intervals. And if the df by dx is increasing, then that would mean that we are approaching a valley. On the other hand, if df by dx is decreasing, then that would mean that we are approaching the peak. So rate of change of function tells us where the maximum value or the minimum value of a function is, or where we have got peaks and valleys within the function. This function can be describing any variable within a structure. Now, in case of single variable calculus, rate of change is very simple, and we can find any two rate of change at close distance to each other, and from there we can determine whether the function is increasing or decreasing. However, the problem comes when we have a multivariable function. So imagine we have got this function which is dependent on two variables x1 and x2. This function is in the form of a surface whose thickness is very small. Now the question comes how to find out the maximum rate of change of this function. We wouldn't know whether the rate of change along x1 or the rate of change along x2 is maximum. Or at the same time, we wouldn't know whether the rate of change in any direction between x1 and x2 is maximum. So the main point is that in case of multivariable function, because the variable is spread along two independent variables, we can't tell right from beginning which direction will give us the maximum rate of change. Hence, we use gradient of functions. Gradient of a function tells us the direction of the steepest descent. In other words, the direction which takes us to the peak in a shortest possible way, or the point where rate of change of function is maximum. In order to determine gradient of a function, we have to first discuss directional derivative. Directional derivative is related to partial derivatives. From calculus, we know that the partial derivatives gives the rate of change of function of x1, x2, x3 in the direction of the three coordinate axes. It seems natural to extend this and to ask for the rate of change of the function f in an arbitrary direction in space. So imagine on the same curve or on the same surface, we have a particular point which is defined by a position vector x, and from this point we are trying to find out in which direction we will have maximum rate of change. Before finding the maximum rate of change, we take a random direction and assume that the unit vector in that direction is n. So the n which is shown on this surface, that is in any arbitrary direction. We take a point and that point is at a position vector x, and from that point we take a unit vector in any random direction and try to find out the value of rate of change. The directional derivative is mathematically defined as follows. Wherever we show the three parallel lines, that means that this is the definition. So directional derivative of this function at a position vector x in the direction of a unit vector n is defined as the value of the function at position vector x plus eta n, where eta is a very small value, minus the value of the function where we started from, that is this point. So f of x position vector and everything divided by eta. Please notice the similarity of this definition with respect to our single variable calculus. In single variable calculus also, we had a function and we took a step delta x, and then we subtracted the value of that function from the point where we started, and then we divided everything by the step size. In here, we are saying that initially we are at a position vector x. We take a step in the unit vector direction by a very small amount. So this is a very small amount which is multiplied with this unit vector. So we slightly move in a particular direction. N is a random vector which is on this surface. Then we subtract it from the initial position vector location, divide everything by this eta, and we make this eta tend to 0. This can be also written as d by d eta, f a function of position vector plus eta n, where eta tends to 0. And this is the same thing as we discussed, that this function can be written as d by dx f of x plus delta x, where delta x tends to 0. So that is the definition of directional derivative. From this definition, we can realize that directional derivative is a concept from a multivariable calculus that measures how a scalar valued function changes at a specific point in a particular direction. So the point is defined by the position vector and direction is defined by this unit vector. So in directional derivative, we are just dealing with the rate of change in a particular direction. So if we have got a function, say defined as x dot x, this is a function which is in a form of x square. So in other words, this function is drawn over here. This is like a parabolic surface. In order to apply this operator directional derivative, in other words, if we take a point, any point on this surface, and we want to move by unit vector n and aiming for finding out rate of change of that function in that particular unit vector, so we can write d by d eta, which is this one, x plus eta n. So this function will become the position vector plus eta n dot position vector plus eta n. So this definition is written for x dot x. Now we multiply both of these brackets, we get x dot x plus 2 eta x n plus eta square n dot n. N and x both are vectors. Once we multiply the bracket, then we can take the differential in terms of d by d eta. So there is no eta in this term. It becomes 0. In this term, we have got eta raised to the power 1, so that becomes 1. And in this one, we have eta raised to the power 2, so it will become 2 eta. Now we apply eta equal to 0 on this expression, and we get 2x dot n. Please note that the final value is always a scalar, as is written over here. And since this is a dot product of two vectors, so that will result in a scalar quantity. The directional derivative of this function corresponding to particular direction n is equal to 2 times x dot n. Now from this directional derivative, how can we find out the maximum rate of change? The direction derivative gives us rate of change in the direction of n, and n is a unit vector. Please note, n has got only direction. Its magnitude is 1. So n will not change the magnitude of this x. N will only change the direction of this x. From our dot multiplication of vectors, we know that if we take the dot product of two vectors and we are interested in finding out the maximum value of the scalar, we have to make sure that the angle between both of them is 0. So in other words, if this unit vector is in the same direction as this vector x, that will give us maximum rate of change. All the other direction will have smaller rate of change. So that gives us the definition of gradient of a scalar field. So gradient of a scalar field, as we have discussed many times, is direction of a maximum rate of change. And for this function, if we take 2x dot n and make the unit vector in the direction of x, we get maximum rate of change. The gradient of a scalar field is defined by partial differential of the function with respect to x1 times e1 unit vector plus partial differential of x function with respect to x2 times e2 and plus partial differential of the function with respect to x3 times e3. So the gradient of a scalar field is actually a vector. As we can see, a vector has got components in particular direction, and we multiply the unit vector corresponding to the axes of our Cartesian system. So we have again the same function, which is f of x. We take the dot product. So this is the given function. We write it in a component form. So we have x1 e1 plus x2 e2 plus x3 e3, and we take the dot product with itself and we apply this gradient formula on it, and we get 2x bar. And that is what we said over here. If we take the vector in the same direction as x, we will get the gradient of a scalar field. Now, the final most important question is, how is the gradient relevant to structure mechanics? Well, we might have realized that gradient can give us the maximum rate of change. So whatever internal force we have, if we know the maximum rate of change, that direction which will give us the maximum rate of that variable, based on that value, the maximum value, we will be able to design the structure. So that can be a maximum acceleration in an acceleration field. That can be maximum stress within a field. We call that a stress field. So just to give you example, if we have a 3D structure as shown over here, and the function which describes this 3D structure, which happens to be a beam subjected to some loading and simply supported. So the function that describes it is f of x1, x2, x3. Again, we apply the directional derivative concept on this, and using the gradient concept, we can find out which location will give us the maximum stress. The area which is subjected to maximum stress will have the tendency to fail,